we will go ahead and start our conversation on sequences and series.
So my question I also noticed that when I got A1 was bigger than A8, and it's just keep going up.
Right.
So I
So
don't
there's
think that was right either.
yeah. So we start developing a logic. In fact, basically the job of our brains is to detect patterns. That is one of its primary functions, and really that goes back to just survival mode. We want to avoid patterns of danger, and we want to find patterns of safety and comfort and food and survival. And so our brain is hyper adept at detecting patterns. So we're going to go and do a couple of examples here. I've listed 3 numbers on the board. We're going to fill in the blank as to what the next number should be. So this first one here, I've got 4, 7, 10. What comes next?
13.
Very good, 13. And I'm getting kind of these looks like Miss Ferris. That is so easy. But to break it down just into a very simple explanation of what we did, how did we know that the next number had to be 13?
Added.
That's right. We're adding 3 every time. If we have a pattern of numbers where we are adding or subtracting, because we can think of it as adding a negative number, if we have a pattern of numbers where we're adding the same number every time to get from one to the next, this is called an arithmetic sequence. And this number that we're adding or subtracting every time, we label D, and that is for the common difference. Here we have another 3 numbers. We've got 4, then 8, then 16. What's the next number going to be?
32.
And how do we know that it's going to be 32?
Because you're multiplying by 2 every day.
Because we're multiplying by 2 every time. So we multiplied by 2, we multiply by 2, we multiply by 2 again. This is called a geometric series. And this number that we're multiplying by every time to get from one term to the next is called the common ratio, and we label it R. So we can see that we are following a pattern, and then we can continue the pattern to find the next number, the next number, the next number. The other thing that's really important to notice about a sequence is that we have a bunch of numbers in a specific order, and everybody's got their place in line. So this guy is first, and this guy is second, and this guy is third, and this guy is fourth. And in this one, this guy is first, and this guy is second, and this guy is third, and this guy is fourth. So this idea of a place in line becomes really important in sequences and series. Very important, can any real number be a place in line? Or if not, what kind of numbers make sense as a place in line? Going back to a conversation that we had all the way back on the very first day of class. Who can think of a real number that doesn't make sense as a place in line? Have you ever been the pi person in line when waiting for, like, to buy a movie ticket?
No.
No. Have you ever been the negative 7th person in line?
No.
I guess if you bought your ticket 7 people ago?
But in some of the wait, did I have one example? In one of the examples had a thing that went like -3, 1, 5.
Now the value could be, this could be a negative number. The value that's in that
Just like
place
the
could be
place.
negative.
Oh, okay.
But when we're talking about the place in line, these can only be counting numbers. And the place in line is indicated with n. N is used a lot in math to indicate a counting number. Yes, but specific, not just x could be any number.
Yeah.
But n specifically is a counting number. This is why, for example, you know, like when you study polynomials, an nth order polynomial is x to the n.
Right.
And as we learned about a little bit, those of you who did 6.2, it's only a polynomial if it is x to a counting number. Can't be x to the -1 or x to the square root of 2 or anything else like that. N is a really important variable in mathematics because it indicates it can only be a counting number. And that makes sense with sequences and series because we can only have positive whole number places in line. We can't be in the 2.5 place in line. We can't be in the square root of 2 place in line. You know, we can't be in the -13th place in line. We can only be first or second, third, so on.
Well, I mean, if like whoever, like the cashier is like waiting for someone like at the very back of the line, then maybe they'll like say, okay, you're the third person, maybe it's like, okay, you're the third person, you're the fourth person, and they really want them to be the 10th person for some reason, so then they're like, okay, maybe you're 9.5, you're 9.
Yeah, no, I mean, you can start massaging it if you're trying to aim for a particular outcome. I mean, I remember that when I was a little kid and getting in trouble. Sometimes when my mom was counting to 3, she would say 1, 2, 2.5.
Yeah.
You know,
2.25.
because she really didn't want the hassle of me getting in trouble either. So she'd give just a little bit of extra time for me to do whatever it was I was supposed to be doing, or to stop doing whatever it was I wasn't supposed to be doing.
But also, once you get to there, it's like, why not just count to 10?
Well, but then if you make the counting longer every time, I mean, at a certain point,
No, but
the axe has got to fall. The consequence
no.
is going to have to.
is that if you're gonna count 1, 2, 2.25, 2.5, 2 3/4,
Yeah.
2 like 2 5/6, like if you do that, like why not just like count to a bigger number and just like stop?
Yeah, but you know that if she had said, if the rule was that I had to do it before she counted to 10, she would get to 9 and I still wouldn't have stopped. I mean, this is what little kids do. They want to see what they can get away with, and they exist in part to push their parents' buttons. So then it would have been the same problem just 7 seconds later. 9.5? 9 3/4?
The illusion of urgency.
9 7/8.
9 11 12? Yeah, so I think we all know what I'm talking about. But so we have two, and this is an important point that you're making here, Gio, is that the value that is in a particular place in line is a sub n. So we've introduced a lot of friends here. We've got n, which is the place in line. We've got a sub n, which is the value in the nth place in line. And we've got d, which is the common difference, or how much we add or subtract to get from one value to the next. And And this starts to feel complicated for something that's very intuitive to us, which is we looked at this pattern, we could see that the next number was 13. It feels like a lot of work to really deconstruct the pieces of the algorithm in this way. However, it's important that we do so, because what if I ask you, what is the 97th value? What value is in the 97th place in line in this sequence? I don't want to keep doing this another 93 more times, because one, I'm certain I will make a mistake, and two, that will be very time consuming and annoying. It'll be much easier once we know what the pattern is to have a shortcut to find the 97th value. And this is how we do it. A sub n is going to be a sub 1, so the first value, plus n minus 1 times d, or the common difference. In an arithmetic sequence, and one that we're getting from one to the next via adding or subtracting, this is how we do it. So if we're going to find, for example, a sub 97, that's going to be a sub 1, which is 4, plus 97 minus 1 times 3. And that we can just,
Why the minus one?
the minus 1, because it's like we've already included the first term, so we have to like back that one out of like the multiplication.
Yeah.
Yes. So that's a really good question. And so this is going to be 4 plus 96 times 3, which would be 300 minus 12, which is 288, plus 4, which should be 292. Somebody please
You're good.
check my math. Okay. So this is much easier than writing out 97 values of this sequence. If we wanted to test to see this is really true, we can test it on a value that we already know. So let's say that we want to find a sub 4. Well, that is going to be 4 plus, this is starting to look, there's too many 4s showing up. Let's take 5, because 5 we can calculate easily. We know we're just going to add 3 to this, it's going to be 16. So a sub 5 is going to be 4 plus 5 minus 1 times 3. This is 4 plus 4 times 3. This is 4 plus 12, which is 16. Check. We can see that it works. So if we want to double check that we've got the right rule, we can always just check it on a value that we already know to see if we have the correct rule. So let's go ahead and test this out. Somebody give me an arithmetic number pattern that isn't too annoying or complicated.
One, 4. Wait, okay, actually, sorry.
Oh wait, yeah, this is about to turn into really the power of
okay.
the power of suggestion is strong.
5, 10, 15, 20, 25, 30, 35, 40, whatever.
Okay, so 5, 10, 15, 20, yada yada yada, yada yada yada. Okay, let's all find the 97th term in this sequence and see if we all get the same number, the same value. that on my calculator.
I don't stop 45.
You did. Does anybody get something different from that? This is good. I want to move on to the difference between a sequence and a series. Does anybody still need any of this that's currently on the board before I erase it to make it real? Okay. So for this particular series, we found that a sub n equals 4 plus n minus 1 times 3. This is a sequence. This is a series. The only difference between a sequence and a series is whether or not we're listing them or we are summing them. If we are adding them together, it is a series. If we're simply listing them in order, it is a sequence. Again, I can pretty easily just put these numbers into my calculator and add them. And in particular, I'm seeing 7 and 13, which is 20 plus 10 is 30 plus 4 is 34. So these numbers are pretty easy to add. But what if we want to add the first 97 values in this series? Again, I don't want to start typing this plus this plus that plus that plus this plus that into the calculator. I will definitely make a mistake. So we have to have a shortcut. One of the things to notice with an arithmetic series, what's 4 plus 13?
17.
What's 7 plus 10?
17.
That's not a coincidence. As you sort of move inwards from either end of a series, you're just adding the same number together over and over. So this is what gives us our shortcut for finding the sum of an arithmetic series. So we have big S for sum. So the sum of the first n values in an arithmetic series is n times, well, I prefer to write it like this, n over 2. So we can either add each of these individually, or we can add 17 together twice. So we take the sum of the first and the last term, and we multiply it by n divided by 2. So this is where that pattern comes from. We can either add 4 plus 7, which is 11, plus 10 is 21, plus 13 is 34, or we can see that we're just adding 17s. We're like adding nested 17s. And so we can just add the first and last value and multiply it by the number of values in the series divided by 2. So let's go ahead and do that with this one. Let's just add the first 97 values. So S of 97 is going to be 97 divided by 2 times 4 plus, what was A sub 97 for this one? We just calculated it.
485 is the other one, right?
Yeah, 485 was for the other one. That's okay if we don't remember. We can calculate it. A sub. Well, I don't want to guess, so let's calculate it.
Yeah.
So we've got A sub 97 is going to be equal to 4 plus 96 times 3, which I think is going to be 292. But can somebody confirm that on the calculator? 292. Okay, so 4 plus 292. So we've got 97 divided by 2 times 296. And we can just put all that in the calculator. What's 97 divided by 2 times 296? Anybody plug this into their calculator? What's 97 divided by 2 times 296? It's going to be 97 times 148, but I can't do that in my head.
1,408. 14,356.
So yeah, so about 100 times about 150 should be about 15,000, which this is. Did anybody get a different answer for this when they plugged it into the calculator? Good. So I'm glad that we didn't just sit here typing in 4 plus 7 plus 10 plus 13 plus 16 plus 19 plus 22 plus 25 plus and losing track of where 97 is along the way and then going back and counting on the screen. It would be a nightmare. So this is why having this shortcut is so helpful and important. So this is what we're doing with sequences and series. We're finding the pattern, we're writing the rule for the pattern, and then when needed, we're adding the values together that constitute part of that pattern. As you might imagine, for a geometric sequence or for a geometric series, the rules are not going to look exactly the same. What numbers do we expect to get bigger faster? Do we expect the numbers to start getting bigger faster in an arithmetic sequence or in a geometric? It's going to be geometric because when we're multiplying, I mean, here we're just multiplying by dinky little 2, and already we can see that this is already getting much bigger than this one. But if we're multiplying by 5 or 10, like these numbers are going to get supersized really quickly. This is why sometimes you'll notice, like in science fiction movies, you know, they'll say, you know, it's like the population of the aliens is growing geometrically. So that word does periodically, keep an eye out or an ear out for it, I guess. But you might have heard it and not noticed it because you didn't have a frame of reference for it aside from just geometry. But it's just one of those things to listen for. Nobody ever is worried in a sci-fi movie because the population is growing arithmetically. That has never been a line in any sci-fi movie.
We should make it one.
Yeah.
How about exponentially?
You heard those oh yeah, exponentially is another one.
I hear that one a lot.
Exponentially is so much scarier.
Yes. But exponentially and geometrically are actually the same. It's the same thing. Yes.
Okay.
So wait, Taylor, you say you heard those words this morning?
I heard those exact words this morning.
In what
The
context?
population is
It
growing
was-
geometrically?
It was exponentially, but same
Yes.
difference. Same difference. It was this book. It's in Chinese, but it was translated very badly.
Oh no.
But it was
Oh,
still
wow.
it's still funny to listen to.
Okay.
It's basically another one of those alien movie knockoffs.
Yeah. No,
But
it's
for some reason they added Squid Game mechanics
Oh.
into the
Wait,
whole thing.
Gotcha.
What?
Okay, well that's a
It is
very
the world's-
aliens are always very popular, and Squid Game is a phenomenon.
It's
So
the world's weirdest crossover, and I still haven't been able to make sense of the plot.
and I'm curious to know whether the authors had a sense of the plot, but you'll have to tell us when you're
Wait, is the
done
problem in
with
the
it. So.
translation, or like would it have made more sense like in Japanese?
That
You know?
seems like
I'm
it's
90% sure it was just generated by an AI and then Google translated.
So you'll notice that all of this stuff about the arithmetic sequences and series, this is chapter 11.2. This stuff with the geometric, this is 11.3. You'll notice when you get to 11.3 that the rule is different and how to sum is different, and that makes sense because fundamentally the process is different, but the concepts are the same. So now I know that there was a particular question that on a particular problem that you had,
Why is this problem wrong?
Yes, which is why is this problem wrong? And so tell me again which problem number this is.
7. In
So this is 11.2, number 7, and what are the numbers that we have in the sequence?
well, no, there isn't a sequence that is, A 8 equals 12, and A 15 equals 61.
And what are our instructions?
Write the rule for that nth term, the arithmetic.
So the problem is with the information that we have right now that we're not given A sub 1 or D. So we're going to have to infer these things. We are, however, we're given A sub 8 and A 15. How many times do we add D? You know, if we add D once, you know, then we're at A sub 9. If we add D twice, now we're at A sub 10. How many times do we have to add D to get to A sub 15 from A sub 8?
7?
Yeah. So, and we're gonna have to do that, you know, so we're doing this 7 times to get from 12 to 61. How can we write that relationship as an equation? So we know
61 equals 12 plus 7b.
yes. Because we start at 12, we add D 7 times, and we end at 61. So now we can use this to solve for D. So we subtract 12, 61 minus 12,
47?
that's 61 minus 14.
49?
Mm. And then we can divide by 7. And so we know that D is going to be 7. All right, but this still doesn't give us A sub 1. But we can use a similar logical process. now we're not just adding b, we're adding 7. So how can we rewrite this relationship between a sub 1 and 12?
Oh. 12 minus, what? 12 minus 7,
Yeah. Is equal to a sub 1. I feel like this is a restatement. I mean, this may be splitting hairs. I may want to start out by saying 12 is equal to a sub 1 plus 7b. And then do that subtraction. But it's the same thing. It's splitting hairs. And so it's going to be 12 minus 49 equals a sub 1. And so what is a sub 1? Going to be
35. Negative 35 and
negative 30. I think it's going to be negative 37. Check me on that though.
37.
12.
37.
Because 10 minus 49 would be negative 39. So 12, so 12 minus 49 would be negative 37. And so now we can plug that in here. And so this is our rule. Now often in the book for the answer they're going to be simplifying it. Meaning we can distribute this 7 and combine like terms.
It's made actually a bit easier, or not easier, but like just the way it's instituted in the book, they had you like replacing like weeks of edge, like with something else, and it's kind of confusing.
Well, there's usually more than one way to get from here to there. So if we're looking at 11.2, let's see what additional ideas. Oh yeah. So yeah, so then this is just using some of the tools that we used in chapter 3, writing a system of equations. And so we could do that. We can do that here as well. So let's go ahead and show this method and see if we end up getting to the same place. So,
Actually the book says at least 4 plus.
okay. But we can show it using a different methodology and that doesn't hurt either. So we could have a sub 6 equals a sub 1 plus 6 minus 1 times d, and we know, oh no, this is a sub 8, sorry. And we know a sub 8 is equal to 12. And a sub 15 is equal to a sub 1 plus 15 minus 1 times d. Which is equal to 61. What is this? this gives us a sub 1 plus 7d equals 12, and a sub 1 plus 14d equals 61. And so then here we can do the substitution method. So we can solve for a sub 1, which is going to be 12 minus 70, and set that equal to 16 minus 14d, and then we can add 14d to both sides, and subtract 12 from both sides, and so we've got 70 equals 49, and d equals 7, and then we can plug that back in here to find a sub 1, and then we can restate the rule. So we can see that it gets us to the same place. I kind of prefer this method just because it makes clear logical, like to me this visually makes really logical sense, like connecting the dots, like how are we getting from each place in line to the next place in line. But we can see that this process here where we're creating a system of equations and then using the substitution method is going to get us to the same destination. It's going to also help us to solve for d and a sub 1. And then we can write the rule. All right. Very good. Did anybody else have any questions from 11.2 that would be helpful for us to answer together? No. Okay.